All right, so let's talk about an asteroid that's coming towards Earth. It's pulling on a Earth is pulling on a 3.5 times 10 to the fifth kilogram asteroid with a force of 1.72 times 10 to the 6 newtons. How far away is the asteroid from the center of the Earth? Solving for the radius, we would basically switch the radius squared and the force of gravity, and then square root both sides. So rearranging the equation, it would look like this. We go ahead and plug in our numbers, which you get from the problem above, and you see that the radius is going to be 9.0 times 10 to the 6 meters. Now the reason I say this is pretty close is because the radius of the Earth is 6.38 times 10 to the 6 meters. It's 6,400-ish kilometers for the radius of the Earth, and this object is 9,000 kilometers away, which is, well, if you think about the surface of the Earth is 6,400 kilometers closer than the center of the Earth. So really this asteroid's only about 2,600 kilometers away from the surface of the Earth. So let's suppose that you and your significant other are sitting on the couch next to each other, and you being the sly person that you is, you kind of scoot a little bit closer to your significant other. Your significant other looks over at you and says, "What are you doing?" And then you say, "Well, I learned in physics that if two objects have mass, they have a gravitational attraction toward each other." And then scoot a little bit closer. Then your significant other looks over at you and says, "Are you calling me fat?" Well, let's actually figure out how much gravitational force would be between the two. So we got mass 1, average male about 85 kilograms, average female about 55 kilograms, and the two are about 1.5 meters apart, which is a good arm's length, arm's width between your hands. So we take the gravitational force equation, we go ahead and plug in our numbers, 6.67 times 10 to the negative 11 times 85 times 55 divided by 1.5 squared, and we get that the force of gravity between you two is going to be 0.000000139 newtons. Well, let's look at this a different way. We have a force of gravity between you attracting you, but what's stopping you from moving together? That would be the force of friction. So let's suppose that we have the surface of your couch is made of the most slick surface we could possibly come up with. There's nothing on Earth that's actually this slick. You don't have two surfaces that can actually have a coefficient of static friction of 0.0001. So let's figure out how much force of friction can be applied, and the upper end of the force of friction is going to be equal to, so the force of friction, the maximum force of friction is equal to coefficient of static friction times normal force, and since you're dealing with a horizontal couch, then that means the normal force is going to be equal to the force of gravity, which is mass times the acceleration due to gravity on Earth, and plug that in and multiply that out, and you get 0.0833 newtons, which is much, much, much greater than the force of gravity between you two. So obviously you're not going to be sliding because there's no surface that's even that slick in the first place. Alright, so Earth is 81 times more massive than the Moon, but it's only 6 times the amount of gravity. Now before we talked about mass is proportional to force of gravity, so 2 times the mass means 2 times the gravity. So why is it that when Earth is 81 times more massive than the Moon, then at the surface of the Moon the force of gravity is only 6 times greater on the surface of the Earth? So looking at this, the mass is not the only thing that determines how strong the gravitational force is. It's also the distance from the center of the object out to where you're measuring your gravitational strength. So if we look at this, gravity is not only determined by the mass of the objects, but also determined by the distance from the centers of their masses. So why is it that even though Earth is 81 times more massive, that at the surface of the Earth it's only 6 times the amount rather than 81 times? Well, that's because the radius of Earth is also larger. And the larger the radius, the larger you are from the center, gravity goes down. So because of the mass, because it's 81 times more massive, it has 81 times more gravity, but because you're further from the center of Earth at the surface than you are at the center of the Moon from the surface, then you're going to have less gravity because of that, and it balances out to only be 6 times as much. So the Earth has a bigger mass, but it also has a bigger radius. Now it's still, the mass wins over and you still have more gravity on the surface of the Earth than you do on the surface of the Moon, but that's the reason why it's not 81 times more gravity at the surface of the Earth than the surface of the Moon. So how much smaller is the Earth's radius? Well, if you actually calculate it out, the Earth's radius would be 3.67 times the radius of the Moon. And mathematically, that's actually, if you take 81 divided by 6 and then take the square root of that, that's where you get the 3.67. And you can come talk to me about that on how we get that if you'd like. So where does the gravitational constant come from? Well, Sir Isaac Newton came up with a gravitational constant using Kepler's laws, using Kepler's equations and data and all the things that he had. But Cavendish later came up with an experiment in order to determine what the gravitational constant is. Now, if you think about the gravitational force equation, there are several things in there. There's the force of gravity, the mass of each object, the distance between the two. So what Cavendish did is he had this fiber right here. Now, this fiber, what it does is when you rotate an object that's hanging from it, it takes a certain amount of force to get it to rotate, and that's called a torsional force. So this light source hits a mirror that's attached to this cable and then hits a scale. So these two masses right here are not even here yet. Just ignore those right now. And you just have this one bar going across with the two masses that's hanging here, and it's able to hang in equilibrium. So everything's balanced. Now, these two masses are then pulled really close to these two masses here, the smaller masses. Now, because of the gravitational force, these two are going to attract large m and small m. They're going to attract closer to each other, which means that they're going to get closer, which means this fiber cable is going to turn a little bit. Well, I can actually measure the mass of each one of these objects. And because the light source is going to move on the scale because this thing is turning, then I can get the torsional force, which is equal to the force of gravity because they're balancing each other. And then I can physically measure the distance between the two masses. So that's mass 1, mass 2. The force of gravity is equal to the torsional force, which can be found by the angle on the scale. And then I can measure the distance between the two. Well, the only thing in the gravitational equation that you have left is capital G. It's your gravitational strength, or your universal gravitational constant. That's the only thing left in that equation. So that's how he actually came up with that value. Kepler's laws. To discuss Kepler's laws a little bit, the first law is that each object that orbits about the sun does so in an ellipse. Now, an ellipse has two foci, and what that means is that the distance from one focus to the ellipse, any point on the ellipse, I can choose this point over here, the distance from here to here, from a focus to this point, that distance is constant all the way around. So if I measure, let's say for example, it's 10 centimeters from here, from one focus to the edge to the other focus, then if I go from this focus to the edge anywhere else, back to this focus, it'd be 10 centimeters still. So it's going to be 10 centimeters no matter what. And that's essentially what Kepler's law was saying, is that at any point we're going to have an ellipse that is equal distance between that object and the foci. Now, Kepler also said that the sun was at one of these foci. So as an object orbits around, it gets closer to the sun and then further from the sun. Now the Earth does this, but the Earth path is actually pretty circular, but it does have a slight ellipse to it. So it does get closer and further from the sun. The second law says that the area that each planet sweeps out is going to be constant. So as it gets closer to the sun, it's going to be moving faster, so it covers a lot more arc length on it, but it's closer, so the radius is smaller. So this area right here is a set value. Now when it's really far away, it's going to be going really slow, so it has a really small arc length, but because it's far away, the radius is a lot larger. So this area, A3, and this area, A1, are going to be the same amount as long as from A to B and E to F are the same time frame. So let's say like 3 days. If this is 3 days here and this is 3 days here, then the area that they sweep in their path is going to be the same. Now Kepler's third law says the ratio of the squares of the periods of any two planets orbiting the sun is equal to the ratio of the cube of the average distances of the sun. Another way of saying that is that the radius cubed over the period squared for any planet going around the sun is going to be constant. Now this is something that actually Newton helped him to explain, but it does hold true that for any planet this is a constant. So one of the example problems we have is to calculate the Earth's mass given the acceleration due to gravity at the North Pole to be 9.830 meters per second squared, and the radius of the Earth is 6,373 kilometers. Now, first thing you should notice is that this needs to be converted to base units. So, gravitational strength equation is the gravitational constant times the mass of the Earth divided by the distance between the center of the Earth and the surface of the Earth squared. We plug that in, and we get that the mass of the Earth is going to be equal to 5.982 times 10 to the 24th kilograms. All right, so the next question we have is, what is the acceleration due to gravity on the surface of Mars? The mass of Mars is 6.418 times 10 to the 23rd kilograms, and the radius of Mars is 3.38 times 10 to the 6 meters. So we go ahead and use the gravitational strength equation again, plug in our numbers, and we get that the acceleration due to gravity at the surface of Mars is going to be 3.747, a little bit more than the gravitational field strength of the surface of the Earth. Next example, it says astrology, that unlikely and vague pseudoscience, makes much of the position of planets at the moment of one's birth to be important. The only known force a planet can exert on Earth is gravitation. So the question I want to ask is, what is the gravitational force exerted on a 4.2 kilogram baby by a 100 kilogram father who is 0.1 meters, about 10 centimeters away at birth? So basically he's holding the child. Well, we use the gravitational force equation, 6.67 times 10 to the negative 11 times 4.2 times 100 divided by 0.1 squared. And we get the force of gravity is going to be 2.80 times 10 to the negative 6 newtons. Now, what's the gravitational force of Jupiter when its closest distance to Earth is 6.29 times 10 to the 11th meters away, and the mass of Jupiter is 1.90 times 10 to the 27th kilograms. So we plug that in, 6.67 times 10 to the negative 11 times 4.2 times 1.90 times 10 to the 27th divided by 6.29 times 10 to the 11th squared, and we get 1.35 times 10 to the negative 6. So actually the father holding the baby has more gravitational force on the baby than any planet would in the process.